the professor is not around this week. Also, he's busy, so he asked me to step in for him. And here we'll quickly go through chapter 1 and look at some of the subsurface exploration processes that you do. I remember in chapter 3 you did a lot of work, like when you calculate the bearing capacity, the settlement, and all that. But then for all the problems you did, you are given like, okay, someone will give you the C, the phi, or the undrained shear strength. But then if you're an engineer at the site, you don't just go and get the parameters out of nowhere. You have to do like some field exploration test, right? For example, you will do the SPT or the cone penetration test to try to get the necessary soil parameters. So for the most part, like, why do we need to do like this type of explorations? Chapter 1. Why do we need to do this type of explorations? It gives you the idea like of the soil condition at the site. Because if you are going to build a structure on a soil, then you need to know what type of soil is present at this location, and then what are the soil properties. For example, when we design the footings, right, we will consider the design or the ultimate bearing capacity is based on the C and the phi, or maybe the undrained shear strength, right? So if you do these explorations, they will give you the data like that, and then from there on you can proceed to do the design. So actually, this probably should have been like more like the chapter 1, but I think the reason why the professor made it after chapter 3 is that so that you can understand the parameters you use in chapter 3, where do they come from? You actually get them from tests like this. And here we have the cone penetration test, and then it is often used to determine the materials in the soil profile and also the engineering properties of the soil. So for example, this is the cone you put in the ground, and then maybe you have a truck there that collects the data, and then here is the cone penetration test. And then usually this angle, the apex angle, is 60 degrees. And then the base area, that is this point, is mostly 10 centimeters squared. And then the frictional sleeve is like this, like the contact between the ground and the cone penetration test. This is the area. And then they just keep pushing it into the ground, pushing it into the ground. So once you are pushing this into the ground, you will get this value, the QC. That is the resistance. Because if you are trying to push something down, the ground will also try to resist, push it back. And then if the soil condition is actually very strong, then this value typically will be higher, right? But if it is not that strong, or it is quite weak, then this value will be lower. Okay, and then also the frictional resistance, it's already punched into the soil. So what is the frictional resistance? What is the contact force between the penetrating cone and the soil? And then also another parameter you can get from this is the pore water pressure. So for the cone penetration test, you can get the pore water pressure. I think earlier you did something about the standard penetration test, right? But then for the standard penetration test, you cannot get any pore water pressure value. But for the cone penetration test, you can get the pore water pressure value. And the SPT usually applied in sandy soils. Okay, so this type of test can give you this value, and then also the pore water pressure, and then also a lot more soil properties depending on what you need and what you are working with. Another tool we have is the vein shear. So this one actually is mostly used in clay soils, and then it is used to determine the undrained shear strength of clay soils. Okay, so we can see here, and then the angle between each of these is like 90 degree, 90 degree, 90 degree. So this is the vein, and then this is the diameter, and this is the height of the equipment. Usually, the height here is twice the diameter of the vein. Okay, and then what they do is like you can see here, they will apply a torque onto this, and then they will keep rotating until the soil fades. Okay, So it's like you go somewhere, the soil is on this top, and then you bore a borehole which is about 50 centimeters. You push the vein shear into the ground, and then you apply a torque at a constant speed. You keep applying at a constant speed until it fails. So once failure happens, then you can determine the SU, which is the on-grain shear strength of clay. So typically, this will give you a very good result in when you are dealing with soft clays and medium soft clays. Okay, it's kind of hard to use it when the clay is very stiff or very hard. But when it's soft or medium soft, then the results tend to be very, very accurate. Okay, so you can get this like the maximum torque. What's the torque, the maximum one you apply here, and what is the diameter, and then what is the height. Then you use this formulation, and it gives you the on-grain shear strength of the clay material you are dealing with. Okay, and this one is the piezometer test, and the other name for it is the borehole lateral test. Lateral as in it's moving laterally, moving outwards. Okay, and then it is used to obtain the in situ deformation and then the strength properties of the soil. So it's like this is a guard cell, this is a guard cell, so nothing can happen here. So this cable will push water or maybe gas into this hole, the hole that we dug already. And then what happens if you put water or gas here? It will expand, right? But the stronger the soil, the expansion will be much slower, right? But if the soil is weaker, then the expansion will be like a lot quicker. So this, you can use it to calculate the deformation, how the soil is going to get deformed, and then you can also use it to calculate the strength properties of the soil. So here you have a lot of formulations that they use to calculate the pressure modulus, the horizontal strength index. So that one is directly from the force you apply. You can get the horizontal stress index, the Poisson ratio. So generally it says is 0.3, and then volume of the probe. So usually this V0 is like the initial volume before you put any water or gas is the V0, and the VM is like after you started putting gas or water into the piezometer, how much volume. So the combination of the initial volume and the VM will give you the total volume of the probe. So this can also typically be used to measure the deformation in the soil, and also it can help you obtain the strength parameters of the soil. Okay, and usually for this case, the soil is considered to fail when the cavity, because when you put this, there's also that the hole already has a size, right? But when the expansion is already about twice the size of this, okay, then you can already assume that the soil has already failed in this condition. And then this one also is another interesting one. It's called the dilatometer. So this one is a little bit similar to this one because they all rely on expansion to determine the soil properties. Okay, so for this case, this is like a membrane, and this is like a sensitive dish. And then once they put it in the ground, what they will do is like, just like the previous one where they put gas or water into the, pump it into the borehole, this one also will pump gas into this. And then the expansion, because if you put gas, this thing will expand, and then it will start pushing the soil. It will push, keep pushing. When the expansion reaches 1.1 millimeter, then they record it. It's like, initially it's 0. They put gas, and then it will keep increasing, until the expansion reaches 1.1 millimeter. Then it is recorded. So you can see, and then this actually can give you a lot of parameters, like it's giving you the K0 here, but you can use it to find the OCR. There are so many equations, the OCR value and the K0 value. This technique is actually used in so many areas. So you can see that K0 is the coefficient of earth pressure determined by the diameter. KD is the horizontal stress index. So this one here is the initial the pressure applied into this, and this one is the forward pressure, and then this one is the vertical stress at the point. You see the effective sigma V0 is the initial effective stress, and U0 is the initial forward pressure. So the P0 is the reading of the diameter because you are putting gas into it, so it means you are applying pressure. And then ID is the material index, so that one also is related by these equations. Then they will just use this to find this value. But then there are so many like formulations and correlations that they can use to find other parameters. For example, the OCR value for clay soils or the undrained shear strength. Okay, and this one is the plate loading test, and it should be similar. Okay, so in this case, you have a base plate, and then this one is like a hydraulic jack, and then it will apply a lot of force on this soil at the bottom, and then determine the condition or the value or the force at which the soil underneath fails. So typically this is more like the ultimate bearing capacity. If you remember, like the ultimate bearing capacity is the maximum force that the soil can sustain until it fails. So this one actually is directly trying to do that. So they will just directly apply the loading onto the soil and then keep recording it until the soil reaches a point that it fails. When it fails, then you know, okay, this is the maximum bearing capacity of the soil. If you can remember, like in the exercises, you have to use a lot of formulations and then try to use the soil parameters or the soil conditions and whatever forces you are dealing with to determine the ultimate bearing capacity. But this is like the field test. They can just directly use this type of condition to determine the ultimate bearing capacity of the foundation or the soil underneath. And you can see the hydraulic jack is already here. And then the reason why they apply some sort of loading onto this is like if the hydraulic jack is giving force, they don't want it to push the beams up. They want most of that force to be pushing downwards. So that's the reason why they have this kind of loading, the vertical loading on top. And then before you reach, for this also, not only can it help you to determine the ultimate bearing capacity, but it can also help you to determine the settlement. Because every time you apply some sort of loading onto the soil, it will settle. Okay, for example, when they say when you apply 1,000, you can see, okay, the soil doesn't fail, but how much? As the, let's say this is the original. Okay, the initial depth of the soil was here, but once you start applying loading, this will keep changing. It will keep changing. The depth will keep reducing until it fails. So by the time the depth is here, you know how much force you are applying. And then by the time it reaches here, you know how much force you are applying. So it gives you an idea as to the rate at which the soil settles. So this one, you can get two types of ratings from it. The settlement with respect to the force and also the ultimate bearing capacity of the soil. Okay, so we can see from the previous ones we did, you can get a lot of the soil properties. For example, those tests can help you find the frictional angle, the cohesion, the undrained shear strength, typically when we are talking about clay soils. And the next one is the groundwater investigation. If you can remember, when you did the footing, there were some problems that you have to consider that underneath the footing there is groundwater, because groundwater actually significantly affects the performance of the soil underneath and even the structure that you are going to build as well. So that's why it is also important to do groundwater investigations. So for this first one is like the groundwater table and the pressure measurement. So you can just measure the groundwater. They just dig a borehole into the ground and then try to find the groundwater level. What is the height of the groundwater level? And what is the pressure at a certain given point? And then this is how the perforated pipe looks like. They will put holes into the pipe and then cover it with this. Cover it with some sort of a fiber. Okay, so this is more like a filter to cover the pipe. Maybe you can try to imagine why, once they have this hole, they have to cover the pipe with a filter. Any idea as to why they may want to cover the pipe with a filter? Because you already have the holes into the pipe, the water can go in. Why do you still need to cover it with a filter?
Make it slower.
That could be, but the main reason is that you don't want the soil particles to go into the pipe. It's right? Because the holes are a little bit big. They are smaller than the soil particles. So if it is too big, then if water starts flowing into the pipe, then the soil particles will also go into the pipe. But you just want to measure the water level, so you just cover it with the fiber to ensure that only the water is going in and not the soil particles. Okay, and the next one is the groundwater table. This one also is pretty similar to the previous one. This one is the piezometer. They are like kind of similar, but you can see the major difference between these two is this one has something here, and it has a seal here and here. And then this one doesn't have any seal. So this one you're just trying to measure the groundwater level and the water pressure inside this well. But for this one, you are trying to determine the water pressure at a specific location. Okay, so that's why at a specific location in the aquifer, so you seal this with a bentonite seal. So this is more like impermeable. Here also it's kind of impermeable, so you can just get the reading for this zone, this area. Yes?
What is a seal? What is the seal?
Oh no, they use bentonite. Yeah, they use bentonite. It's a chemical material that they can use to seal. Like it's usually used in excavation, especially if there is a lot of water coming in. They'll use the bentonite to stop water from going in. I just need to have a picture here that seems to not. Okay, I'll try and find it later. Okay, and this other one is also like the field permeability test, trying to see or get the hydraulic conductivity of the given soil at a site. Because one thing also is that it is very important to know how quickly or how slowly water flows through the soil. Most of the time when we are just dealing with using the calculations with hands, probably usually don't use the hydraulic conductivity values, but when you are doing more complicated analysis to determine like the ultimate bearing capacity or the condition of the soil, you will also consider the permeability of the soil. That is how quickly or slowly water can flow into the soil. And then here you have like two different types of tests that are actually conducted to determine the hydraulic conductivity or the field permeability. So here you can see it is a constant pair. So they just keep adding water with a flow rate of Q to maintain the raising water level in the borehole. So the water level is already here. They will try to evaluate how much, at what rate we can put water so that this head stays the same. It does not decrease or go up. Because this layer is permeable. If you put water here and you stop, what will happen? The water will go down because it will flow to the other areas. So the QC or the Q determines the rate at which you can put water here so that this height here doesn't change, it remains constant. If you get that Q, then that will give you the hydraulic conductivity or the Q of this test section. Because if here the hydraulic conductivity of this is 10, if you put 10, then this one will stay the same. But for example, let's say the hydraulic conductivity here is 10, and then you are putting it at a rate of 5. What will happen? This head will go down, it will reduce. Or if you are putting it at 20, but this is 10, what happens? This head will increase. So they start trying to find that constant head. At what value does this head stay the same? So that will give them the idea or a better understanding of the hydraulic conductivity of, or the permeability of this layer. So usually when we talk about the permeability, in sandy soils the permeability is quite higher, but then when you deal with clay, then it's typically very, very slow. It takes, can be extremely painfully slow. Okay, and then this other one is called the variable head test. So in this case, they don't try to keep the head constant. What they do is like, water is added at the beginning of the test to raise the water level in the borehole. So this is the initial water level, and then they add water up to this height. And then what happens? The water head will fall. It will keep reducing. Okay, and then this is the initial. This is the time at 0. The time at 1 when you add water up to this height, and then the initial height, and then the new height at time equal to 1. So you can use this to actually calculate what is the hydraulic conductivity of this soil, right? For example, if H1 is, let's say the height is about already 10, and then at this point is 5 meters. So your time 0, the initial time, let's say, okay, assume that this is just 0, and then the time it takes from here to here is about 10 seconds, but you still need to keep this positive. Then you just minus, and then you get meters per second. So that will give you the permeability or the hydraulic conductivity of this layer of soil. Like that is how quick water flows through it. So, but this A or B, which one you choose, sometimes also depend on the field condition or the people who are doing the performing the tests at the site. Okay, and this one also is quite similar to the other one, but the technique is just a little bit different. So it's also used to determine the permeability of the soil at the site. So here, this is the pumping well 1, pumping well 2, pumping well 3. And then what they do, you can see a similar illustration here. 1, 2, 3, these are observation wells, and then this one is where the water is pumped out. So just like the previous one, this one also aims to find the values for the hydraulic characteristics of the geological formations through which the groundwater is moving, so through the soil layer. So you can see here, water is pumped out. If water is being pumped out, the water level here will also reduce. But it will reach a point, like maybe this place is far enough that the water level still stays constant, it stays the same. So by using this equation, let's say the distance from here to here, R2, and then the distance from this well to the other well, R1, pi over h squared. So the H2 is this head, and the H1 is this head. The change is more like a gradient problem. And then you can get the K, which is the permeability of the soil layer in that zone. Okay, and then you can also see there's a Q, that is the flow or the discharge of water. So usually, as the water is flowing from here, it goes into this. This is a triangle here to measure discharge. So this discharge rate can just be calculated Q, and then can be inside here to determine the permeability of the soil. Okay, so we've already looked at some of the tests that can be used to determine the groundwater level, the pore water pressure, and also the permeability, as well as how to determine the properties of soil. For example, if you want to find the frictional angle, the sea or the shear strength. Now we look at the geophysical surveying, that is the electrical and electromagnetic survey. So usually this type of surveys are done to try to find out that what is the material underneath or below the ground. Because mostly on the surface of the ground you can get an idea as to the material you have. But if you go down, you can't see. So you need to have some sort of a technique that can be used to help you analyze and evaluate the properties of the materials underneath. Okay, so this is more like a carrying out the resistivity image profiling survey. And here, it says the approximate rate of resistivity of some common geological materials. So some sort of power is pushed into the soil, and then these are the resistivity values. For example, if the resistance falls between this range to this range, then you know that, okay, this material underneath is probably more like an igneous rock. Or if the resistivity value falls here, it is a metamorphic rock. And then for clay, the value is smaller. So it's like the harder the material, the higher the resistivity value. And then the weaker the material, the lower the resistivity value. So with a table like this, if you push the electric signals into the ground and then you get the resistivity values, you can have an idea, okay, what type of material is located in this zone or below the soil surface. Okay, and the next one is like the seismic surveys for earthquake problems. So the seismic surveys can be used to locate the depth of strata and evaluate dynamic elastic properties of soils and rocks. So if you are trying to do dynamic analysis, in some places you probably don't have to worry about this if you don't have earthquakes. But in places like Taiwan, they will typically do this a lot of the time. They will do the seismic surveys to try to understand the soil condition and the resistance or the layers and the various stratas of the soil properties and the rocks. So this is the material they use, and then they will put like some P waves into the ground. And then the velocity will differ based on the material that the wave is passing through. Okay, so if it is just air, the wave, the minimum value is from 0.31 to the maximum of 0.36. And then you can see as the material gets harder, like you see granite, the value is higher. Metamorphic rocks is also a bit higher. As the material gets harder, the value gets higher. So this is like, you can always have this type of references when you are going to do like tests like this. And then they will all give you an idea as to what type of material you can expect to have underneath the ground. Okay, so basically, once you've done each of the tests mentioned above, you need to write a report and an interpretation. Because for the most part, like the people who do that, you will probably be hired by someone to do the field investigation or to oversee. Probably, like if you are an overseeing engineer, there will be people on the side who will do the investigation. But then you have to go there and then oversee and make sure that everything they are doing is actually being done according to the required standards. And then once you get the value, it is your responsibility to make sure that you write the report in such a way that it is understandable and it is quite easy for the other ones who are going to do further work at the site to better understand it. In some cases, once they finish the field investigation, they will still go to the laboratory tests. I think it depends on the nature of the project. If it is a very big project, they get the data and whatever from the field investigation. They will take the materials and the samples to some sort of a laboratory to try to perform further analysis and experimentations to get more accurate values. So if you're going to write a report, it says you have the general description, the analysis, and the audit. So for the general description, number one is the purpose of the project and its importance. So if you're going to write a report, it is important to state what is the project for. And why is it important? Because for different projects, the requirements may be different. It's like if you are going to build a 2-story building or you are going to build a 50-story building, the requirements are totally different. So you have to give a good description of the project and its importance. And then also the topographical features and the hydrological conditions of the site. So they need to know what are the hydrological conditions, like the permeability of the soil at the site, and also the soil topography. Okay, a brief description of the various field and laboratory tests carried out. So in your report, you need to write a brief description of the field investigation. For example, if you do SPT, you need to give a brief introduction, like what is SPT, what did you do, and how the process went. Or if you do the CPT, it's the same thing. You have to give a brief description, and then what are the tests that you do. Okay, so you will also see the boring log or the CPT. I'm not sure if you have an example for this. Oh yeah. So this is more like, you also have to include something like this into the report. For example, the corn penetration test is like, okay, you are pushing the corn into the ground. And then the QC, that is the resistance at this point, it is going to change with depth. It is going, so you can see the resistance here is very little. But as you go down, the resistance here gets bigger. So this gives you an idea that the material here is actually quite different from the material here, and this is stronger. And then here you can see, okay, you can assume that this is the same material because the resistance is pretty much very much the same. And then you get here, you can see you have a very, very hard material because the resistance gets a lot more. So you see here too, it's pretty similar. This is the friction. Why will the friction be higher? Because you are dealing with a harder material. So all these kind of things need to be included in your report for reference. And then this one also, the CPT, because you can also use the CPT to get the, when you're doing it, to get the pore water pressure. So you can get how the pore water pressure changes with the depth of the soil. Okay, so results like this, figures like this, all need to be included in your report. Okay, and then also the geophysical surveys. For things like geophysical surveys, also it depends on the scale of the project. If it's a minor project and then you want to do like some very, very complicated field investigation processes, maybe the owner will not even listen to you. They'll go and find a new engineer. Okay, and the table listed with the testing results. So you can give a table and then what are the test results for each of the tests that you have conducted. And then the second part talks about the analysis and discussion of the test results. So if you obtain the test results, you just don't put it there like that. You need to kind of explain. They need to be explained in detail so that anyone working on the project, once they see it, they know what the table is about. What is the results referring to? Not just put it on a piece of paper. Maybe if you see it yourself, you will know what you are referring to. But if someone new comes and then tries to take a look, they have no idea what you are trying to say. Okay, and then you also determine the soil profiles, like the soil layers, the geotechnical and the hydraulic parameters. So what are the geotechnical parameters? For example, the soil condition like C5, SU, and the hydraulic parameters, for example, K, the permeability. Okay, and another part of your analysis can be determine the allowable bearing pressure. What is the maximum bearing pressure for the soil at the site? And also, for example, if you are dealing with piles, you can talk about the pile load. And then 4 talks about the evaluate the soil liquefaction potential. This one also is probably location specific. Like if it is in regions where they have earthquakes, like for example in Taipei, a lot of places actually in Taiwan, they try to do the liquefaction potential map so that people know like the areas where they are staying, whether the soil is liquefiable or not. So soil liquefaction actually is typically like mostly happen in sandy soils. So it's like during an earthquake when the ground is shaking, the soil, instead of behaving like a solid material that is strong, it behaves like water. It's just like water. So it's like it has no resistance, it has no force. So most of the structures underneath will probably fail in that type of situation. So you need to evaluate the soil liquefaction potential so that you can also take that into consideration when you are building the structure. Okay, and then also analyze the excavation-induced influences. So if you're just doing a footing, maybe you don't need to worry too much. But if you're in the middle of Taipei, you are trying to build a 50-story building, you need to dig a very big hole, or you need to excavate a large area into the ground. But you have a lot of buildings nearby. So you have to take that into consideration. If I excavate this area, the buildings nearby or the structures nearby, how is it going to influence those areas? Because if you don't take proper measures, the excavation in your site will collapse and the nearby buildings will also collapse. Now you have a much bigger problem. Recently, I think about 1 month ago, it was a big news in Taipei. Do you guys know where is Nehu? Yeah, there was like a big construction project and then the excavation collapsed. So the nearby buildings, some of the buildings, the fourth floor become B1. So a lot of buildings nearby have a problem. So you can imagine how much problem the company will be in. Because anyone whose building has a problem, they will have to compensate them or come up with some sort of settlement for them. A lot of buildings got affected. It's probably 1 month ago, it was a big news in Taiwan. So it is important when you do projects like that for you to analyze the excavation-induced influences. Like you remove a big area of the ground, but there are still a lot of forces coming. So in a lot of places, if this is the excavation, you excavate a big area, they will put some sort of struts to support the structure, to make sure that it doesn't collapse inside. But you need to know like maybe what are the buildings nearby, what are the structures nearby in order to provide enough support for this so that the structure will not collapse. If you did not take proper measures, then you may find yourself in a very, very big problem. Okay, and the orders, so for example, you can make recommendations. For example, if the groundwater level is too high, you can ask them to dewater. So they can seal a certain area of the excavation and then try to dewater, remove the water before they continue excavating again. And then ground improvement. So if the soil condition is actually not good enough, they can also use some techniques to improve the condition of the ground or the soil. And then also, depending on the soil condition, you can also make suggestions as to the construction procedures. What construction procedure will be most ideal for this site? Okay, and then maybe you think, okay, the soil condition is XYZ, but to make like some conclusive conclusions or to give very valid suggestions, you need to conduct further tests. Like maybe you need to do X, Y, Z to be on the safer side or to better understand the soil condition or whatever it is that you want to understand at the site. So all of these are the responsibilities of the engineer that is going to write reports. So you have to put all this into consideration. Okay, so here it is referring to like some of the tables that you will or you need to include in your report. So this one is a boring log, like you bore something into the ground. And then this is the depth. 1 meter, 2 meter, 3 meter, blah, 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 up to 11 meters. And then the sample number. Each of the samples at each layer will be numbered. And the SPTN blow, you did that. Like what is the blow count at this layer, at this level, at this level, at this level. And then the description of the soil at this point. So you can see the USC classification. And then you have to give the particle size distribution, like the gravel, the soil, medium or whatever clay. And then you give the water content, the density, the specific gravity. So with a table like this, when you give it to anyone, they directly know what they are looking for. Right? They know like what type of information they need. They can easily get it from here. But if everything is mixed up, then it's harder for other engineers to go through it. Okay, so we did the CPD result. This is the groundwater observation. This is the resistivity imaging profile. So they try to take an image profile of the ground based on the resistivity. So you can see this layer, the colors are pretty much the same. And this layer also, the colors are pretty much similar. So this gives you an idea that these and these are what different soil layers. So all this type of information can actually be included in your report. Okay, so we just finish this and then that will be the end for today. So it says the summary and general comments. When you are designing a subsurface exploration schedule, a list of properties for design or calculation should be summarized. What is it that you want? You cannot go to the field without having a general idea as to what you want to investigate, right? And each investigation method has its purpose, advantage and disadvantage and applicability. So you need to understand, okay, why do you want to choose this technique to determine the soil parameters or the soil profile instead of the other one? There are advantages and disadvantages, and it depends on the problem you are dealing with. So a good geotechnical engineer needs to use them with great caution. Okay, the report should be well and detailed compiled, which will provide a useful and important information for viable design. So when people look at your results, they should be able to obtain all or most of the information they need to perform their design. The field testing should be supervised to assure that test specifications are obeyed. So most of the time, you don't need to do the test yourself. You oversee people who are doing it. But they typically don't care much. They want to do it as quick as possible. So you need to make sure that you oversee them and then make sure that they do it to the required standards. And then laboratory testing should follow the specification, instruction, and the work process should be carefully recorded. So every work process should also be carefully recorded. And then the accredited laboratory are sometimes required essentially. Maybe you may need further tests to understand the soil condition. So after doing the field testing, you probably also need to do the laboratory tests to better understand the soil condition. So this is all for this chapter. I think what you need to understand is like just get a basic idea of how each of these instruments works and then what they are used to perform. That's enough. Yeah, like the formulations and all that, probably not that important for now, but you should understand how the equipments work, what they are used to do and all that. Okay, so we stop here for today. Have a good day. Thank you.